अस्सलाम वालेकुम एवरीवन। हम फिजिकल इलेक्ट्रॉनिक्स का सेकंड लेक्चर है जो मैं आपसे शेयर कर रहा हूँ। इसमें अगर डिस्प्ले अच्छा ना हो तो मैंने आपसे पीडीएफ शेयर किया हुआ है ना इस फाइल का, तो ये इंशाल्लाह आखिरी क्लास होगी जिसमें डिस्प्ले का इशू आएगा। इसके बाद डिस्प्ले के इश्यूज नहीं आएंगे। तो हम स्टार्ट करते हैं इसको। आज जो हमारा लेक्चर है फिजिकल इलेक्ट्रॉनिक्स का, वो लेक्चर नंबर 4 है। और एज यूजुअल मैंने गूगल क्लासरूम का जो कोड है वो यहाँ पे लिख दिया है, जहाँ पे आप इस लेक्चर के दौरान मैं जो पेजेस लिखूंगा उनकी पीडीएफ ले सकते हैं। और आज का जो लेक्चर है, इससे पहले हमने लेक्चर आई एम सॉरी, इसको मैं रीस्टार्ट करता हूँ इस वीडियो को, उसमें थोड़ा सा इशू था एक। आज जो हमारा लेक्चर है फिजिकल इलेक्ट्रॉनिक्स का, वो लेक्चर नंबर 4 है। और एज यूजुअल मैंने गूगल क्लासरूम का जो कोड है वो यहाँ पे लिख दिया है, जहाँ पे आप इस लेक्चर के दौरान मैं जो पेजेस लिखूंगा उनकी पीडीएफ ले सकते हैं। और आज का जो लेक्चर है, इससे पहले हमने लेक्चर 3 तक चैप्टर नंबर 1 जो था फ्लॉयड की बुक का, उसके कंटेंट्स डिस्कस किए हैं। और हमने अभी तक ये डिस्कस किया है कि अगर हम एक प्योर सेमीकंडक्टर मटेरियल को एक साइड से ट्राइवेलेंट इम्प्यूरिटी के साथ और दूसरी साइड से पेंटावेलेंट इम्प्यूरिटी के साथ डोप कर दें, तो हमारे पास एक पी एन जंक्शन बनता है सेंटर में। और दोनों, उसका जो प्योर सेमीकंडक्टर मटेरियल प्रीवियसली था उसके एक साइड पे ज़्यादा होल्स मिलते हैं और दूसरी साइड पे ज़्यादा नेगेटिव चार्जेस मिलते हैं, आई मीन इलेक्ट्रॉन्स मिलते हैं। आज का जो हमारा होगा लेक्चर, उसका फ्लो कुछ इस तरह से होगा कि सबसे पहले हम पढ़ेंगे डायोड के बारे में और उसके बाद डायोड बाइसिंग पढ़ेंगे। ये डायोड्स लफ्ज बेसिकली मैंने इसलिए लिखा है कि ये जो फ्लॉयड की बुक का चैप्टर नंबर 2 है उसमें हम मजीद डायोड्स भी पढ़ेंगे, लेकिन सबसे पहले हमारा जो हमारा टारगेट है वो है पी एन जंक्शन बेस्ड जो डायोड है उसको हमने डिस्कस करना है। उसकी बाइसिंग है, बाइसिंग क्या होती है इसके बारे में बात करेंगे, वी आई कैरेक्टरिस्टिक कर्व ऑफ द डायोड एंड देन डिफरेंट डायोड मॉडल्स। प्रोबेबली हमारे इस लेक्चर में हम ये तीनों चीज़ें कवर कर लेंगे इंशाल्लाह। और इसके बाद जो लेक्चर होगा हम उसको रेक्टिफिकेशन से स्टार्ट करेंगे। तो स्टार्टिंग विद today's lecture, it is about the diode initially and few more things about the diode. We should remember this picture we already had discussed. इस पिक्चर में एक प्योर सेमीकंडक्टर मटेरियल को डोप किया गया है लेफ्ट साइड पे ट्राइवेलेंट इम्प्यूरिटी से, जिसने इसमें बहुत से होल्स इंट्रोड्यूस करवा दिए हैं। और राइट साइड पे हमारे पास इसको डोप किया गया है, और राइट साइड पे हमें इसमें डोप किया गया है, एक्सक्यूज मी प्लीज, यस। तो राइट साइड पे इसको हमने डोप किया है एन टाइप मटेरियल के साथ, आई मीन पेंटावेलेंट इम्प्यूरिटी के साथ, जिसने इसमें बहुत से इलेक्ट्रॉन इंट्रोड्यूस करवा दिए हैं। और हमें ये भी पता है कि जो होल है जहाँ पे जो पी टाइप रीजन है उसमें कुछ माइनॉरिटी चार्ज कैरियर्स मौजूद हैं, मतलब कुछ इलेक्ट्रॉन्स हैं। और इसी तरह से जो हमारा एन टाइप रीजन है उसमें भी कुछ माइनॉरिटी चार्ज कैरियर्स, मतलब कुछ होल्स मौजूद हैं। आई होप इट इज क्वाइट विजिबल टू यू। आई एम जस्ट introducing few minority charge carriers there to make it more practical. और ये जो स्पेस इन बिटवीन है जहाँ पे मैंने कोई चार्ज शो नहीं किया, हम इसे डिप्लीशन रीजन कहते हैं। और ये बेसिकली एक ऐसा क्रिस्टल है जिसकी एक साइड पे एक तरह के चार्जेस हैं, दूसरी साइड पे दूसरी तरह के चार्जेस हैं. So I can say it has two different ends. From here we encounter the term diode. तो हमारे पास जो डायोड है ये एक ऐसा सेमीकंडक्टर मटेरियल के जो इस तरीके से हमने उसे डोप किया है कि उसकी अगर एक साइड कंप्लीटली नेगेटिव है दूसरी पॉजिटिव है तो इसको हम कहते हैं, इस स्ट्रक्चर को हम कहेंगे कि डायोड है. इस पे बेस्ड जो डिवाइस बनेगी वो डायोड होगा. और इस डायोड का एक सिंबल भी है जो हम अपने लिटरेचर में यूज करते हैं. मैंने ये जब मैंने बेसिक लेक्चर्स आप लोगों से शेयर किए हैं जो इंट्रोडक्टरी, उसमें हमने डिफरेंट इलेक्ट्रिकल कंपोनेंट्स के सिंबल्स को देखा है. उसमें डायोड का सिंबल ये था. इस डायोड का ये वाली साइड है, फॉर एग्जांपल इफ वी टेक इट एज अ ट्रायंगल, तो ये इसका वर्टेक्स है और ये इसकी साइड है. तो ये वाली साइड जो है ये बेसिकली शो करती है पी टाइप साइड ऑफ द डायोड को, और ये जो वर्टेक्स है इस तरफ ये एक तरह से ये शो करता है एन टाइप साइड ऑफ द डायोड. तो ये हमारे पी एन जंक्शन बेस्ड जो डायोड है ये उसका सिंबल है. और ये उसी डायोड की हमने इंटरनल स्ट्रक्चर जैसे लिखा हो कि इंटरनली ये कैसा होगा. अब हम बात करते हैं इस डायोड की बायसिंग के बारे में. तो मैं बताना चाहता हूं कि हम ऑलरेडी ये डिस्कस कर चुके हैं कि डायोड जो है ये यूनिलेटरल इलेक्ट्रिकल कंपोनेंट है. ये यूनिलेटरल इलेक्ट्रिकल कंपोनेंट है. यूनिलेटरल का मतलब है कि जो करंट को सिर्फ which allows the flow of current in one direction and forbids in the opposite direction. तो यूनिलेटरल कंपोनेंट है ये डायोड. ये करंट को सिर्फ एक तरफ अलाउ करता है मूव करना. और हम जानते हैं कि अगर ये एक डायोड है इसमें से कोई इलेक्ट्रॉन्स फर्दर क्रॉस नहीं कर सकते इस पोटेंशियल बैरियर को या इस डिप्लीशन रीजन को कि वो होल्स से मिल सकें, unless we apply some energy from the external source. ये एनर्जी एक्सटर्नल सोर्स से जो हम अप्लाई करेंगे, हम इसको हीट एनर्जी की बजाय या मैकेनिकल एनर्जी की बजाय हम चूज करते हैं इलेक्ट्रिकल एनर्जी. जो एक्सटर्नल एनर्जी मैंने इस डायोड को प्रोवाइड करनी है, अगर वो इलेक्ट्रिकल एनर्जी है तो मैं अगर इसको समझ लूं कि मेरे पास एक डीसी सोर्स मैंने अप्लाई कर दिया है इसके साथ, तो इसके साथ जो डीसी सोर्स मैं कनेक्ट करता हूं डायोड के साथ, इस प्रोसेस को हम कहते हैं बायसिंग ऑफ द डायोड. सो लेट्स make a heading here, biasing of a diode. Well, we shall now disclose this picture I have drawn here, and I should as well apply a voltage source here. और मेरे पास जो वोल्टेज सोर्स है वो मैंने इस तरह से अप्लाई कर दिया है. कन्वेंशनली ऑल ऑफ अस नो दैट दिस is the positive terminal of the voltage source. The larger line is the positive of the voltage source and the smaller line is the negative sign of the voltage source, where these holes are the P region of the diode and these conduction electrons are the N region of the diode. Well, furthermore, I would like to introduce a few minority charge carriers here to make it more practical. Well, these are few minority charge carriers here and these are few minority charge carriers here. Well, when we apply this potential across the ends of this diode, they are connected at the like terminals. I mean, the positive of the battery is connected with the P region of the diode and negative of the battery is being connected with the N region of the diode. So this means we have connected the like terminals of the diode with the like terminals of the voltage source. Such a combination of such a combination of voltage and the diode is called forward biasing. Like why we call it forward biasing, I shall now discuss it in detail. Forward biasing means the current is allowed to move in forward direction. For example, the negative terminal of the battery will repel these electrons and they will move towards the depletion region, and this positive terminal of the battery, this also repels the holes towards the depletion region. Well, when electrons are forced to move towards the depletion region and holes are forced to move towards the depletion region will be occupied by a few of the electrons and by a few of the holes, and the width of the depletion region decreases. This is the sole idea to explain that why current is allowed to flow in one direction. I mean, if depletion region is narrowed, it is easier for the electrons to cross this barrier, or it is easier for the holes to cross this barrier. Otherwise, that means if we make a forward biasing of a diode, it will allow the current to pass through the diode. I mean, in case of electrons, it is the counterclockwise, and for the positive charges, it is the clockwise. So, in forward biasing, if I would like to draw the current and voltage graph, I can do it. Let me please write down a few terms here before we move further. Well, the voltage source, the potential source has the potential of V, where the current I goes through this diode. So knowing this information, we can draw an IV curve of the diode. What does this IV curve mean? It means the independent quantity, which is the voltage, is on x-axis, and the dependent quantity, which is the current, is on y-axis. So if I connect the voltage source in such a way that the like terminals of the voltage sources are connected to the like terminals of the diode, then the current will pass through it. And this permission to the current to pass through it is like this. For example, if I enhances the voltage, the current also increases. So this graph looks like this. Initially, the amount of current increases very slow by increasing the voltage source, but later the current increases very rapidly by increasing the voltage. This is actually explained on the basis of the potential barrier. So I can say, initially when I applied the voltage source, the potential barrier was there. But when this battery overcame the potential barrier, the amount of current is now increasing because there is no more barrier there. That's why after initial few changes in the voltage, we get a very sharp peak of the current with a very minor change in the voltage. Such a combination of the diode with the voltage source is called forward biasing. Let's talk about another combination, and that is reverse biasing. We are reading the biasing of the diodes. Let's talk about the reverse biasing. what does this term means? Reverse biasing mean if I have the same diode, let me introduce few minority charge carriers to make it more practical. Well, there are few minority charge carriers and there are few minority charge carriers in the N region as well. Well, let's talk about another type of biasing that is called the reverse biasing, in which we apply the opposite terminals of the voltage source with the opposite terminals of the diode. For example, I have connected positive of the DC voltage source with the N region of the diode, and I have connected the negative of the DC source with the positive or the P region of the diode. By doing so, what I am asking the diode to do, or asking this crystal to behave like, is that the positive and negative attract each other. So I'm asking the electrons to go away from the depletion region, Similarly, I'm asking to the holes to be attracted towards the negative terminal of the battery and go away from the depletion region. What it causes, it actually increases the depletion region. The increase of depletion region means it is even tougher for the electrons to cross through this region. It is tough to cross through this region for the electrons or for the holes. That means in reverse bias, we have no current at all, because it is not easier for the charges to cross this much barrier. So if I draw the IV curve in the reverse bias, let me show it on the negative axis, because I have applied the opposite polarity of the voltage source than the previous one. So it is V here and it is I here. Well, if I choose to draw the VI characteristic curve, V is independent. It may vary as much we want, but the current is dependent on the voltage. So as long as I keep on changing the value of voltage in the reverse bias, there is no current. In fact, practically there is a very few current, and that very few current is because of the minority charge carriers, because they are being repelled by this positive and by this negative. So they happen to cross this potential barrier, and they offer a very little current. So in literature, you may find a very small current there, even in the reverse bias, but that current is termed as a leakage current. It should be a point of interest that we can say the other way, that the current is being stopped because there is a huge amount of resistance there. So I mean, if there is no current at all after applying the potential difference across the terminals of the diode, that means that there is a large amount of resistance there. This large amount of resistance should have increased the temperature of this device. If the temperature is being increased, this of course will cause more and more electron-hole pairs, thermal electron-hole pairs, and by increasing the temperature, we may cause to damage this device. If it is being damaged at very, very high voltage, of course, and that very high voltage is about 18 to 20 volts. So if we apply 20 volts DC in the reverse bias, we may have a burnt diode. That burnt diode means there will be a large of current there, and this current, also called the avalanche current, from the term you can imagine that what does it mean? That there is a large amount of current in the reverse bias only after a certain value of the voltage applied, and such a voltage is called breakdown voltage. Such a voltage is called breakdown voltage. Well, this breakdown voltage is about 18 to 20 volts for the silicon-based diodes, and it means that diode is no more perfect device. It has now damaged, and we shall replace it with a healthy diode. Well, after discussing the biasing of the diodes, we shall now discuss the diode models. Let me tell you about diode models that in literature we use 3 models of the diodes, which are very easy to remember. There are 3 models of the diodes. 3 models of the diodes. These models are being divided into 3 categories based on the simplicity or the practicalness we introduce in it. The first one is called ideal diode model. I would like to explain this at this moment that there is no such device called ideal diode or a practical diode or a complete diode. The other 2 terms, the practical diode, and third one is the complete diode model. These are actually in theory. The diode has nothing to do with these models, but the way we like to solve a problem in hand, if we choose the problem to be very practical, we should go to the complete model. If we want to make some assumptions to make the problem easier, we should go to practical diode. And if we want to look the problem very easy, at the basic level, so we should go to the ideal diode model. Let me tell you, what does it mean? We shall explain it with the diode structure, with the diode symbol, and later the IV characteristic to differentiate between these 3. Let's talk about the first one and then we will move further after completing the discussion of ideal diode model. Let me tell you, ideal diode model is, for example, if it is connected in forward biased, well, I should let you know on which basis we are going to discuss these 3. We shall discuss it on the basis of difficulty in the circuit. So we shall discuss every type of diode on the basis of 2 different circuits. The first one is forward biased and the other one is reverse biased. So forward biasing and then the reverse biasing. And I would try to stay on the same page to complete this discussion, so it is summarized in short place. Well, I would like to tell you that forward biasing means a diode has been connected with the voltage source in such a way that positive terminal of the diode is being connected, or the P region of the diode is being connected with the positive terminal of the battery and N region with the negative terminal of the battery. Similarly, if a diode is connected in such a way that P region is being connected with the negative terminal of the battery and N region is being connected with the positive terminal of the battery, so such a combination is called reverse biasing, and this combination is called forward biasing. For example, if we are supposed to discuss these 2 on the basis of simplifications we want, I would like to start with the simplification first. This circuit will turn into another circuit when we replace this diode with the ideal diode model. So it is actually the diode is being replaced by a short circuit. You probably can see there is a complete line there. So ideally, a diode is being converted into the short circuit. Let me please join this line here. Well, these are the 2 points from where I had removed the diode with the ideal model of the diode. I have replaced it with the ideal model of diode. In forward biasing, an ideal diode means that in forward biasing, it is being replaced by the short circuit. So, if there is a short circuit, which means the resistance is zero and the current should be infinite. Well, if I draw the IV characteristic curve, in forward bias, it should look like this as I am drawing here. Let me please choose another color to show it if I can, or I will move to the next color if it is not visible to you, as it is not. It is actually the yellow color. If it is not, no problem. We shall choose the green color and I should explain it. See, even if there is no voltage applied, I mean a very small voltage is applied, the diode is being converted into the short circuit and there will be an infinite current. Well, in the case of reverse bias, this diode is being replaced by what? Let me do it for you. It is being replaced by an open circuit. And as we know that in open circuit, there is an infinite resistance, so there will be zero current. So if I choose to draw the IV characteristic curve for the ideal diode model, I should keep it to zero to infinite. So there is no current at all. Whether we are increasing the voltage in the reverse bias. So this is the ideal diode model. I mean, in summary, ideal diode model converts into a short circuit if it is connected in the forward biased, and it is being converted into the open circuit if it is connected in the reverse biased. That means there will be an infinite current or a large amount of current in forward biased, and there will be zero current in the reverse biased. Now moving to the second one, that is the practical diode model. I should draw a line here to separate the place for the discussion of the remaining two. The practical diode model now, as we can see in forward bias, it will be connected like this, that P terminal of the diode is being connected with the positive of the battery and N terminal of the diode is being connected to the negative terminal of the battery. So in this case, in practical diode model, we have introduced a bit of the difficulty or bit of the practicality, in fact. So in practical diode model, a practical diode model in forward biased is being converted into what? Let me draw it here for you. It is being converted to a voltage source of how much value? Of 0.7 volts in case of silicon-based diode. What is it? I should explain it a bit, and I'm sure you're gonna get it. That if we apply a potential difference across the diode in forward biased, what will it do? It will, of course, behave as a potential barrier there. And this potential barrier we earlier discussed arose from where? From the closely packed charges in this region, and they actually have their internal electric field which opposes the flow of these electrons, and to overcome that field we need to apply some external electric potential, and this is that potential. If this potential is of 0.3 volts, then it cannot cross this potential barrier, because the value of this potential barrier for the silicon based diode is 0.7 volts. So this diode converts into an opposite battery of 0.7 volts when connected in series with the battery in forward biased as a practical diode. So practical diode model means the diode is not being replaced with the short circuit, rather it is being replaced with a voltage source which opposes the applied voltage with a value of 0.7 volts, which means it has some potential barrier, which is more practical when we discuss the diodes, rather making it just a short circuit. So now we have introduced a bit of practicality in the diode, that it has some potential barrier, and that potential barrier of course will base on the material it is made of. If it is silicon based, then it should have 0.7 volts potential barrier, and if it were based on germanium, it should have 0.3 volts potential barrier. The main thing is the diode is not being replaced with the short circuit because it is not practical, it is not the actual situation. The actual situation is that there is a potential barrier there, and we need to apply some large voltage larger than this potential barrier which opposes the applied voltage source. So this happens when we introduce a little bit more practicality in the diode model in our theory. So the practical diode model, if we draw the IV characteristic curve, that should be interesting to draw. And let me tell you, in the forward biased, if we apply the voltage source, then the amount of current can be seen in such a way that there was no current at all to a certain value. What was that certain value? That was 0.7, after which there was an infinite current. So this value is the potential barrier. For the silicon based diode, it is 0.7 volts. For germanium based, it should be 0.3 volts, and it should vary for every other material, whether they are compound diodes or the elemental diodes. So this current is again infinite as it was here, but this was at 0 volts and it is now at 0.7 volts, because to that value of the voltage there was no current at all, because there was a voltage source opposing it. Well, moving towards the reverse bias of the practical diode model, let me tell you that what happens exactly is, we are doing what? We are discussing the reverse biasing of the diode in the practical model of the diode. I mean, if we are encountering a diode and we are supposed to make some calculations in a problem and the diode is connected there, we should do what? We should take it as open circuit if it is connected in the reverse biased. So we can see this, that in the reverse bias it has the same effect as the ideal diode model, which means ideally if there is a diode, then the IV characteristic curve can tell us what will we have if we connect a diode in reverse biased. So it is V, and this is the current I in negative direction. Let me show you how will it look like. We will apply the force, we will apply the potential difference, but there will be no current at all. To a very large value, well, keep remember All this can happen only within the boundary I just had told you about, and that is the breakdown voltage. Of course, at the breakdown voltage, we will have infinite current there. And moving towards the complete diode model, we should discuss it as forward biasing and then in the reverse biasing. In forward bias, if we increase the more practicality or the difficulty level of our problem, and we has decided to make the problem more real and more practical, then we should move towards the complete diode model. Complete diode model means that this diode will be even more practical when connected in circuit, and we have to make some equations. We should keep this remember that now we are going to discuss the forward bias of complete diode model. The important point is that we should know what we are going to discuss is the forward bias, and we are going to discuss the third model of the diode, and that is the complete diode model. Let me tell you how will it behave in the circuit if we have to develop a theory based on complete diode model in forward biased. So this diode will be replaced with a voltage source as stated earlier, which opposes the applied voltage and will have some internal resistance. This internal resistance is called RF. That means forward, the resistance of the diode when it is connected in forward biased, or otherwise in some books you may encounter to see it as RD prime. The small letter shows the variable resistance, and the prime also shows the same thing. Well, let me tell you that here was the place where the diode was connected in forward biased, and that forward biased will be considered as a voltage source which opposes the applied voltage source in the forward biasing, and there will be a small resistance there in series with this potential barrier. So together these two, this V and this battery and this resistance makes the diode. Actually, these two components have been replaced for the diode to take the complete model of the diode in account. So seeing this, as I told you, this resistance is also variable. So what will we have? If we draw the IV characteristic curve, we should expect our result to be, I'm going to draw it for a certain value of the resistance which is constant. Otherwise, I should have to draw a curve there. So if there is a V, that is potential difference applied. I'm sorry, I should have mentioned here. At the same time, I should have mentioned here that this voltage source, it may be called as VF, that is the potential barrier in the forward bias. If not, then we can say FVB, that means barrier potential. So I would choose the VB because in your book, VF is the term we use for the biasing voltage. So VB is the terminal, is the barrier potential of the diode. Here it is again VB, and V is the potential applied across the ends externally. Well, how will the graph look like? The graph will look like initially I should use a marker here to make it visible like this, and then a straight line like this. This is the practical model of the diode, the complete model of the diode we should take into account while talking about the forward biased. And now if we are talking about the reverse biased, let me tell you how does it behave. In complete diode model, the diode is being replaced by a resistor connected in parallel called R prime. that is the reverse biased resistance and with the open circuit here. And there is no, there is no potential barrier there, but there is a parallel resistance connected there. This causes a small, because this value is very large. So what we have is, because this value is very large, so if I choose to draw the IV characteristic curve, I should draw it this way. Let me please mention the variables first. And in the reverse bias, if I choose to draw the IV characteristic curve, excuse me please, I should choose this color. Well, it will slightly decrease. It will have a slight current there because of this varying the large value of resistance. Of course, these three plots have been drawn within the range of this breakdown voltage. The voltage has not been exceeded this breakdown voltage. Has it exceeded, we should have a breakdown voltage and the damaged diode with an avalanche current there. We had not discussed it. Well, as a quick review, the lecture 4 was about the diodes, their biasing, and 3 diode models. It depends on the problem or the question that which model is suitable to discuss or to take into account. I hope this lecture was clear. If there is any confusion, any ambiguity, you're more than welcome to ask through your CR or in the question answer session we will have, inshallah. Thank you very much.
Okay. Well, I hope आप लोगों ने ये जो वीडियो सुनी है इसमें कुछ बातें समझ आ गई होंगी आपको. एक्चुअली जब मैंने स्टार्ट की ये वीडियो रिकॉर्ड करना तो मैंने शुरू के 10 मिनट ऐसे ही बोलता रहा अंग्रेज़ी में, फिर अंग्रेज़ी ख़त्म भी हो गई तो मुझे ख्याल आया कि मैंने इतनी देर अंग्रेज़ी में बोला है कि अब मुझे इसी में बोलते रहना चाहिए, इसलिए ये वाली वीडियो सारी ऐसे ही बनी हुई है. तो आई होप अगर आप लोगों को कोई मतलब ऐसी, क्योंकि असल में इसमें ना लिखते हुए 3 चीज़ें इकट्ठी कर रहे होते हैं. मुझे लिखना भी था, मुझे बोलना भी था और मुझे अपने कैमरे पे भी ध्यान रखना था कि वो रिकॉर्ड कर रहा है ना. तो इट वाज अ डिफ़िकल्ट सिचुएशन, सब कुछ चीज़ें इकट्ठी जो है ना लेके चलना. इस वजह से आपको कुछ पॉजेज लगेंगे और कुछ ग्रामेटिकल मिस्टेक्स लगेंगी जो मैं बोल रहा हूँ उसमें, और कुछ थोड़ी बहुत डिसकंटिन्यूटी शायद होगी, शायद थोड़ी थोड़ी कहीं पे है, मैंने जब इसको सुना है साथ साथ. अच्छा, मैं थोड़ी सी 1-2 बातें क्लियर कर दूं. तकरीबन 35 to 36 मिनट्स के दरमियान आई वाज टॉकिंग अबाउट कंप्लीट डायोड मॉडल. कंप्लीट डायोड मॉडल में जो मतलब डायोड्स में बेसिकली इस पूरे सब्जेक्ट में जो लोअर केस आपकी क्वांटिटीज़ हैं, मतलब जो देखें छोटी ABC जो हमने यूज़ की है उसकी 2 वजूहात होती हैं. आमतौर पे वो AC क्वांटिटीज़ होती हैं या फिर जैसे इस केस में है कि ये रेजिस्टेंस एक्चुअली बहुत ही स्मॉल रेजिस्टेंस है उस रेजिस्टेंस के मुकाबले में जिस सर्किट में हमने डायोड को कनेक्ट किया होगा. फॉर एग्जांपल हमारे पास एक वोल्टेज सोर्स होगा, एक डायोड होगा और फिर एक रेजिस्टर होगा. वो जो रेजिस्टर होगा एक्सटर्नल रेजिस्टेंस, उसकी वैल्यू बहुत ज़्यादा होगी, उसे हम कैपिटल R से लिखेंगे और इसको हम स्मॉल r से लिख रहे हैं. और दूसरा जो प्राइम इसके ऊपर है, इसका मतलब है टाइम वेरिंग क्वांटिटीज़ हैं, ये टाइम के साथ वेरी कर रही हैं. तीसरी बात, मैंने इस प्लॉट में अगर आप देखें तो ये बेसिकली ओहमिक प्लॉट है. ये वाला रीजन जो है ये ओहमिक ग्राफ का रीजन है, ओहम्स लॉ में जो होता है, जिसका मतलब है कि एक स्ट्रेट लाइन तब आती है जब हमारी रेजिस्टेंस कांस्टेंट है. तो हमारे इस पर्टिकुलर प्लॉट में कंप्लीट डायोड मॉडल में भी ये जो RD है ये टाइम वेरिंग नहीं है, टाइम के साथ बदल नहीं रही. अगर टाइम के साथ बदलती तो फिर ये कर्व जो है ये ऐसे स्ट्रेट लाइन ना होती बल्कि ये भी कर्व्ड होती. तो हमारा जो एक्चुअली ये जो ग्राफ हम देखते हैं IV का, क्योंकि ये हमें एक्सपेरिमेंटली पता चलता है, डायोड को तो नहीं पता कि मैं इस वक्त कंप्लीट मॉडल में हूँ या प्रैक्टिकल में हूँ या आइडियल में हूँ. डायोड तो सिर्फ उस पे आप एक पोटेंशियल अप्लाई करेंगे। जगह जगह बाय द वे मैंने वोल्टेज लफ्ज बोला है, दैट मीन्स पोटेंशियल, कि जो आप पोटेंशियल डिफरेंस अप्लाई करते हैं एक्सटर्नली। पोटेंशियल डिफरेंस आपने अप्लाई किया और उसके साथ हमारा जो करंट में कुछ चेंजेस आए, आप उनको रिकॉर्ड करते गए। फॉर एग्जांपल एक टेबल की फॉर्म में 0 वोल्टेज पे 0 करंट है, फिर 0.1 वोल्ट्स पे कितना करंट है, 0.2 पे कितना है, 0.3 पे, एंड सो ऑन। तो उन पॉइंट्स को जब आपने इस ग्राफ में प्लॉट किया तो ये कर्व बनेगी ऐसे खुद ब खुद। ये जो हम बना रहे हैं, ये सब चीजें हम एस्टिमेट कर रहे हैं कि अगर डायोड ऐसा होता तो फिर उसका ग्राफ ऐसे बनता। एक्चुअल सिचुएशन ऐसी कुछ नहीं है। आई होप यू गाइज अंडरस्टैंड इट। तो अब मैं इंशाल्लाह इसके जो नेक्स्ट वीडियो है वो प्ले करता हूँ। बिफोर दैट मैं इसको पॉज करता हूँ रिकॉर्डिंग को, वो उसकी सेटिंग कर लूँ जो मुझे करनी है। थैंक यू। ओके, ये मेरा नेक्स्ट लेक्चर था जो मैंने रिकॉर्ड किया था, तो इसको मैं अब प्ले करूँगा आपके लिए। तो इंशाल्लाह आई होप इसके एंड तक आप फर्दर जो है वो क्लोज आ चुके होंगे उस जो हमारा प्लान है पढ़ने का, जिन चीज़ों को, कि डायोड की एप्लीकेशंस एज इन अ रेक्टिफिकेशन सर्किट। तो आई विल नाउ प्ले इट फॉर यू इन अ व्हाइल।
of the lecture series of physical electronics। और आज के जो लेक्चर है इसमें हम जो चीज़ें डिस्कस करेंगे, लेक्चर फ्लो जो है वो कुछ इस तरह होगा। पहले पार्ट में हम डिस्कस करेंगे डायोड मॉडल्स के बारे में, कुछ जो हमारा प्रीवियस टॉपिक में भी एंड पे हमने कुछ डिस्कस किया था इसी बारे में, उसी की कंटिन्यूएशन है। और सेकेंडली हम डिस्कस करेंगे रेक्टिफिकेशन, और उसमें हम हाफ वेव रेक्टिफिकेशन पढ़ेंगे इंशाल्लाह। वेल, हमें प्रीवियस लेक्चर में हमने क्या देखा था, मैं वहां से थोड़ा स्टार्ट ले लेता हूँ। प्रीवियस लेक्चर वाज द लेक्चर नंबर 4, और लेक्चर नंबर 4 में हमारा जो लास्ट टॉपिक था मैं उस पर जाना चाहता हूँ। और उसमें हम पढ़ रहे थे, हमने डायोड मॉडल्स पढ़े थे, आइडियल डायोड मॉडल, प्रैक्टिकल डायोड मॉडल और कंप्लीट डायोड मॉडल। हमने देखा था कि फॉरवर्ड और रिवर्स बायस में इनके जो प्लॉट्स हैं वो किस तरह बनते हैं और इनके इक्विवेलेंट सर्किट किस तरह बनते हैं। आज हम इसी की कंटिन्यूएशन में ये देखेंगे कि जो हमारे 3 डायोड मॉडल्स हैं इनमें जो इक्वेशंस हैं वो किस तरह से वेरी करती हैं। So, without wasting any time, I would like to start. I would like to start with the first diode model, and that is the, sorry, we could have seen this, the diode models continuation. And first of all, we are going to discuss the ideal diode model. और आइडियल डायोड मॉडल जो है, अगर हम उसको फॉरवर्ड बायस में देखें तो इनिशियली जो बायसिंग है किसी डायोड की, उसका मतलब है कि डायोड के पास हम एक बैटरी, एक वोल्टेज सोर्स कनेक्ट करें और साथ ही एक लोड रेजिस्टर है। आइडियल डायोड मॉडल में जो इक्विवेलेंट होता है इस डायोड का फॉरवर्ड बायस में वो होता है शॉर्ट सर्किट। शॉर्ट सर्किट का मतलब है कि इसमें फॉरवर्ड बायस में VF इज द वोल्टेज ड्रॉप इन फॉरवर्ड बायस्ड। तो फॉरवर्ड बायस में इसमें जो वोल्टेज ड्रॉप है, लेट मी प्लीज टेक इट अ लिटिल क्लोजर, ब्रिंग इट लिटिल क्लोजर टू योर to my mobile screen to make it more visible, as I have written with the pen ballpoint mistakenly again, which I was supposed to write with the marker. So, if we start discussing the forward bias of the ideal diode model, so in ideal diode, in forward bias, an ideal diode model behaves like short circuit in forward bias. So, applying KVL on this circuit, we have got V bias and we have got no voltage drop here but a voltage drop here across RL. So I should have written the polarities of the circuits. those who are aware of the polarities, they can understand it well, but who are not, they should at least listen 1 or 2 lectures of my basic electronics series, and the lecture number 6 and 7 can be helpful in this regard. So this is the voltage source. According to it, we put the polarities in the direction of conventional current, with as current goes from positive to negative terminal. So we apply the polarities on the load resistor as positive and negative as current flows from top to bottom in the RL. Applying KVL in this closed circuit, as we know, the Kirchhoff voltage law says that the sum of the voltages in a closed loop is 0. So V bias is the input voltage, and the voltage is being dropped across the load resistor, and as from Ohm's law, we know V is equal to IR. So rather writing V R load, we are writing IF, which is the forward current, multiplied by load resistor is equal to 0. So the formula for the forward bias current with a load attached, if an ideal diode model is being considered, is V bias over RL. So the current only can be limited by the value of R load or R limit. We occasionally call it R limit as well, or the R load. Well, if we talk about in reverse bias, let me move a little forward that in reverse bias, the diode is connected in such a way that positive terminal of the battery is being connected with the N type of the diode, and negative of the battery is being connected with the P region of the diode. Well, in reverse bias, an ideal diode model behaves like open circuit. So if we see this open circuit which has an infinite resistance, so applying KVL in reverse bias, let me show you that it will behave like this. Please do not concentrate on this side of the paper, as I'm hiding it on purpose to get things mixed. Well, ideal diode model in reverse bias behaves like an open circuit. If we apply the KVL, there is an infinite resistance here in the open circuit and a small resistor in comparison with the infinite resistor is the load. So it is V bias minus IR, and infinite resistance here, which gives us equal to 0. Excuse me. Thank you. Well, so if we make the subject the IR, we take it on the one side and rest of the things on the other side, it is V bias over infinite resistance, which gives us 0 ampere current. So in ideal diode model, forward current is calculated as V bias over R load or R limit, and the reverse current is 0 because of this open circuit. So moving forward, we have to now discuss the practical model of the diode. And in practical model, we mean that as in forward bias, the practical model, the diode is being replaced with a voltage source, that shows the potential barrier, and that is called VF, potential barrier in forward bias. Applying KVL again, by the way, here it is load resistor. Unfortunately, it is not quite visible, so I need to make it a little visible here now, and it is the R load. So applying KVL, we have to put the polarities across the resistor only, because there are two potential sources and they have their fixed polarities already. So applying the polarities on this resistor load, they are positive and negative with respect to the V bias, as the positive terminal of the battery is connected here, and it will allow the conventional current to pass through clockwise. So in clockwise direction, we need to apply positive here and negative here. So using KVL, it is V bias minus VF minus IFRL is equal to 0. Taking IF on one side, we will have V bias minus VF over RL. That means IF has a fixed value, but it has a little less value than it had in the case of ideal diode model, because VF is being subtracted from the V bias. So IF will be little smaller than the IF we've calculated earlier. I mean, the forward current is being a little bit decreased for the same input value of V bias. Well, now talking about a reverse bias of a practical diode model, if we connect negative of the battery with the P region of the diode and positive of the battery with the N region of the diode, and there is a load resistor there, this diode in practical diode model will be replaced with an open circuit in the reverse bias. So using the same calculations we had done earlier for the ideal diode model in the reverse bias, we can repeat the same values and we can get the reverse current, which is 0 amperes in case of practical diode model as well. Moving forward to the third diode model, which is complete diode model, if we discuss it in forward bias. So let me make it clear that I am going to use the same circuit, but I will repeat. I will replace this diode with the complete diode model. So taking this figure in mind, keeping this figure in mind, we should know that there is V bias, there is R limit or R load, and there is a diode. This diode, you will see, will be replaced in complete diode model with a voltage source and a small resistor. This RD prime is the small dynamic resistance of this diode, which is actually the kind of internal resistance. It is actually the internal resistance, but it is being called the dynamic resistance. That's why we have put RD prime here. Well, VF is the potential barrier in this case, and V bias is the applied voltage, and RL is the load resistor. Applying KVL here, we have got 1, 2, 3, and 4 components connected to our voltage sources and to our resistors. So we have got V bias with respect to this minus VF. Let me put the polarities here, positive and negative, positive and negative. These polarities are being applied as per the direction of the conventional current because of V bias. So taking IFRD prime and IFRL, taking IF common, we have got V bias minus VF minus IF into RD prime plus RL prime is equal to 0. So if I take IF on the other side, I will have V bias minus VF over RD prime plus RL. It shows that IF will be varying with the value of RD prime, which of course varies over the span of time. So as we apply VF, the RD prime will keep on changing if V bias is going to increase. So we have got a little lesser current in complete diode model in forward bias than that of practical diode model, which already had a little lesser current than that of the ideal diode model. So talking about the reverse bias now, let me tell you, probably you already knew this, that RD prime, the dynamic forward resistance, is much, much smaller than the load connected here or the limit resistor here. So actually RD prime is very, very smaller. And moving further, if I discuss the reverse bias of the complete diode model, so I will replace this resistor with the complete diode model in reverse bias, which is actually an open circuit with a large resistor R prime in reverse bias. It is, sorry, RR prime is in parallel with the open circuit. If we consider the complete diode model in a reverse bias, so applying KVL, we can have IR, which is V bias over RL plus RR prime. Keep remember that RR prime is much, much smaller than the load resistor, which actually means RR prime is the resistance in the reverse bias, and it is very, very high resistance in case of complete diode model, where it was even infinite in case of practical sense. In case of complete diode model, where it was even infinite in case of practical.
ओके सॉरी, यहाँ पे जब मैंने बताया कि आर प्राइम जो है वो आर एल से बहुत ज़्यादा है, मैंने कहना था, गलती से मैंने कम कह दिया। तो आर आर प्राइम इज लार्जर देन आर एल।
Practical and ideal diode models. So this was all about the diode models. If I again bring in front the diagram, we had the IB characteristic curves of the diode models. They should be in accordance with these equations, and we can see that there is a large current in forward bias with the application of very small value in the forward bias, and in reverse bias it is zero, whatever the value of the V reverse V bias is. But keep remember, all this discussion is being supposed within the breakdown voltage range. And in the practical diode model, as we have seen, the current is lesser, a little lesser earlier, and that was lesser as of VF, which is in case of silicon-based diode is 0.7 volts, which I had mentioned earlier here. And in reverse bias, it has a zero current as well. But the complete diode model, the current was varying, increasing but varying because of the RD prime. Because of the RD prime, and in the reverse bias, the current, we had a smaller value of current. You can see the deviation from this red line. Red line are the axis, and black line is the current. The value of current on the graph. So we have a small current in the reverse bias. Even in the reverse bias, if we have the complete model, because of this resistor, it is a large valued resistor, but it is not infinite, as was the case with practical and ideal diode model. So we actually had verified our graphical results with our mathematical equations, and now I will move towards the next entirely different topic of our discussion, and that is actually the part of the applications of the diodes, as the chapter name was the diodes and their applications. So first part of this lecture has been over in just about 17 minutes, and we have a lot of work to do, which is about the rectification. So I will start with the basic definition, that what is rectification. So I would like you to take a pause here and to think what rectification is and why do we use it. It is page number 2 of lecture number 5. Well, lecture 5, page number 2, and the topic, of course, is the rectification. rectification. I am sure many of you, almost every one of you, have heard this term earlier in your previous classes, and the term rectification means the process of converting an alternating current signal to a direct current signal. So what is it? It is a process of converting AC to DC, where AC is the alternating current and DC is the direct current. And we should keep remember that in most of the electronics components, we require the DC current. So we need to have such a circuit which can convert the alternating current to the direct current. So let me tell you, this is the rectification. And what is the rectifier circuit? A circuit which converts a circuit which converts AC into DC. That again means alternating current to the direct current. Let me tell you one more thing that, we'll see this sooner, that what AC current is and what DC current is. So let us have a plot here. This is the time axis and this is the current axis. If we have such a current, a sinusoidal wave, we can see here the magnitude of the current as well as the direction of the current keeps on varying. Periodically, such a current signal is called AC, alternating current. And this is the current our generators produce. AC generators produce such current. Now, we should think about the direct current first before moving forward. Well, direct current should have one and only one direction. It should not change its direction. And if it is our time axis and these are our current axes, the direct current ideally should be a fixed values, constant amount of current which flows in the same direction. It always stays positive or it always stays negative, depends on how we measure it. So if, for example, I0 was the amount of the current here, it will remain the same in case of direct current. And this is the case. The solar cells are the devices, or the DC batteries are the devices which produces the direct current, and as our major source of electricity are the generators, and most of the time in our electrical components, electronic based devices, we need the DC current, and for that we need to convert AC into DC, and this is being done by using the diodes. So this is technically the first application we are going to study of the diodes. So I will draw here a circuit called half wave rectifier. So if I give a heading here of rectification, I will now, well, half wave rectification will be defined after seeing it practically, or working here on the pages. So to do this, we need to do what? We need to plot a circuit here. For example, as I had told earlier in the prerequisite lectures of the basic electronics, which I shared with you as well, that this is the symbol of the AC source. And well, if I have this source connected with a diode and a load resistor, and it ends up here. Well, now we have an AC source, a diode connected here, and a load resistor here. And what I will do, I will take the output at load resistor. So we shall be ready to discuss it as we have already learned the working of the diode. Well, first of all, I would like to draw the input signal, and input signal will be drawn in quarters or in halves. For example, as I told you earlier, that this is the waveform AC current typically have. So if we talk about the input, I will take the input with a red pen and I will draw the output with the green one. And basically I will use these three markers for the input signal, the black, blue and red. But output will be drawn only with one, and that is the green one. So let us talk about first half cycle. As every one of us knows the term half cycle, so I will draw the first half cycle here. This is the first half cycle of this sinusoidal wave. And by the way, this graph is not of current but the voltage. So I will be taking the voltage on the y-axis and the time on the x-axis. So let us see what will happen on this circuit if we apply this first half cycle. Well, there will be a positive polarity here of this AC source and a negative here because we have got a first half cycle, which means the upper half is positive, greater, and the lower half is smaller in the number. So we have got a positive here and a negative here. And if we apply the polarities and we see how the diode is being connected during the first half cycle, we have got positive of the battery connected with the P region of the diode, and negative of the battery with the N region of the diode. So the diode is in forward biased. Forward biased during first half cycle. Well, what will happen? Consider this diode as the ideal diode model. So it has zero forward resistance, and we will get some output here, and that output will exactly be equal to the input signal. So on output, I will have a half wave of same magnitude and same time duration. For example, the magnitude is V0 and it will be V0 here as well. Let us talk about the second half cycle, which I'm going to draw with the black marker here. This is the second half cycle. And we can see now this value is greater than this value. So the polarities as shown with the black marker here for the second half cycle are positive and negative. Well, it is the first half cycle, and now we are discussing the second half cycle. In second half cycle, we can see that negative of the battery is being connected with the positive, P region of the diode, and positive of the battery is being connected with the N region of the diode, which gives us what? It gives us reverse biased during second half cycle. It is the first half cycle, it is the second half cycle. So in reverse bias, if we take the ideal diode model here, it will be an open circuit. An open circuit drops all the voltage and load will drop nothing. And nothing here means the zero, as I'm supposed to draw the output with the green pen, so it shows us 0. Similarly, in the third half cycle, again with the red, it is the third half cycle. The polarities will again be positive and negative, and this positive negative makes it forward biased again. First and third half cycles have forward biased diode, and we will have some output here. And if I draw the output here, let me please allow to reduce the period a little bit here to make sure the diagram is completed within this range. And in the fourth half cycle, we will have again the polarities of positive and negative, which means positive and negative. Positive is being connected with the N region, and negative of the battery is being connected with the P region. So we have got second and fourth half cycles have the diode in reverse biased, and the output will be 0 on the load because all the signal will drop across the diode because of the infinite resistance. So it should be interesting to see that half of the cycle, half of the voltage is being passed through the diode and is being seen on the output, but the other half is being dropped across the diode because of the reverse bias, and there is 0 value seen at the output across the load resistor or the limit resistor. And then again, the next half cycle, it is forward biased, and we can see it in the output across the load because of the ideal model of the diode, and the 0 again for the fourth half cycle because the diode is in reverse bias. And ideal diode model, we have seen that this is open circuit. So open circuit means all the voltage is being dropped here and nothing can be seen on the output as we are seeing this. Well, this is interesting to know that there is no negative half cycle. This is clear that there is no negative half cycle, but a positive half cycle and 0. Then positive half cycle and 0. As half of the wave or half of the input signal is being wasted or is being dropped across the diode and there is nothing on the output. So we call such a circuit which actually allows one half cycle and forbids the other half, actually drops it across the diode, and we have nothing in the output for the other half cycle and so on, the second, fourth and sixth and so on. Every even half cycle we have nothing in the output across the load resistor. Such a circuit is called half-wave rectifier circuit, and such a process is called half-wave rectification. Here are a few important points we should keep remember, and one of them is that is it DC or not? So I must say that it is DC, but there are pulses of the DC, so it is pulsating DC. There is no direct current which has a fixed magnitude. There are pulses of positive, but it is not going to alter its direction. So we call it DC, but these are actually DC pulses, not a complete DC. And we will see in the upcoming lectures that we need to have some more components, some extension to this circuitry to get a complete DC circuit, get a complete DC output as we had expected to get. But at least we now have a current flowing in the one direction only, and its direction is not going to alter. So it is no more AC but DC, but its magnitude, as it is being fluctuated a lot, so we call it the DC pulses, not the DC. Well, let me tell you one more thing, that there are few points we should know. There are few quantities we shall know when we are talking about the rectification, and these are few terms. The first one is cycle, the other one is time period. Though I'm not going to revise these terms, but I would like you to revise them from some source, from your previous books or from internet, if you are not well aware of these terms or these terms are not very clear in your mind. Well, next, there are a few typical terms we should know, and I will probably be talking about these now. The first term is peak value. Well, the peak value means the maximum value here on the crest, or otherwise we can say the maximum amplitude it has. The signal has the amplitude of the signal is actually the peak value. And then there is peak inverse value. Well, the peak inverse value means the diode can withstand a maximum value in the reverse bias, and of course we measure it in terms of the applied signal. For example, if I have applied a signal of plus 5 volts to minus 5 volts, or the plus 5 amperes or minus 5 amperes, I should actually have written it in terms of voltage as it is here. So if I have plus 5 volts here and minus 5 volts here, so the peak inverse value means, as the diode is in reverse bias for the second half cycle and its maximum value is minus 5 volts, so this minus 5 volts is the peak inverse value in this signal and in this circuit. And then the C is the average value. As we have seen that peak value means the maximum value or the amplitude of the input signal, that of course will be the output signal if we take the diode as the ideal diode. And Average value gives us a little bit better result, and we will see the average value, and we will actually calculate the average value in the next lecture for the half wave rectifier circuit and for the full wave rectifier circuit. And then we will have another term, and that is root mean squared value. As we know that if we talk in terms of AC signal, its mean will be 0, but we want to have its value, so we take the mean of the squared values and then take the square root to convert it into the original signal. So root mean squared values actually are a point of interest for us when there are AC signals there. So these are few terms, and we will be discussing these terms. But there is an extra term called the ripple voltage. We will see that. What is that? Because that is not the part of rectification circuit, but it is coming when we talk about the AC to DC conversion. So that is it about lecture number 5, and I hope if there will be any questions, you will be very comfortable in asking, and I will definitely be answering it in question answer session, or when you tell me through your class representative, or you send some comments on it, I shall respond to that in another video lecture. Thank you very much.
ओके वेल यहाँ पे एक दो बातें मैं आपको बता दूँ. फर्स्ट ऑफ ऑल पीक वैल्यू की जब मैं बात कर रहा हूँ तो यहाँ मैंने एक टर्म गलती से बोल दी थी, जिसमें मैं कह रहा था मैक्सिमम एम्पलीट्यूड. एम्पलीट्यूड इटसेल्फ इज मैक्सिमम. या तो मैं इसे कहूँगा मैक्सिमम उसकी जो मतलब वैल्यू है, और या मैं कहूँगा एम्पलीट्यूड. एम्पलीट्यूड इटसेल्फ ये लफ्ज़ खुद ब खुद मैक्सिमम को शो करता है. और एक टर्म यहाँ पे मैंने नहीं बताई है, वो है पीक टू पीक वैल्यू. पीक टू पीक वैल्यू का मतलब है कि इस क्रस्ट से लेके ट्रफ के दरमियान जो मैक्सिमम वैल्यूज में शिफ्ट है, +5 और -5 की पीक टू पीक वैल्यू होगी 10 वोल्ट्स. और इसी तरह से जब हम करते हैं पीक इन्वर्स वैल्यू, तो पीक इन्वर्स वो वैल्यू है जो रिवर्स बायस में डायोड पे ड्रॉप होती है मैक्सिमम, वो उसकी यानी कि पीक. तो रिवर्स बायस में ये हाफ सिग्नल है, तो इसका मतलब है कि रिवर्स बायस में इस केस में जो हमारी पीक इन्वर्स वैल्यू है वो -5 वोल्ट्स है. तो उसके बाद हम बात कर रहे थे एवरेज वैल्यू. एवरेज इज़ क्वाइट अंडरस्टैंडेबल. और रूट मीन स्क्वायर्ड वैल्यूज़ आप तब लेते हैं जब एसी सिग्नल्स के साथ आप प्ले करते हैं, बिकॉज अगर आप एसी सिग्नल का मीन लेंगे वैसे ही या एवरेज लेंगे तो वो 0 आ जाएगा. तो आपको इसके स्क्वायर्ड वैल्यूज़ जो हैं उनका मीन लेते हैं ताकि उसकी नेगेटिव जो है ना वो ख़त्म हो जाए. +5 -5 0 होने की बजाय आपको 25 और 25 को आप ऐड करें फिर स्क्वायर रूट लें तो वो उसको मैग्नीट्यूड तो सेम हो जाता है, लेकिन उसका नेगेटिव पार्ट ख़त्म करने के लिए हमें रूट मीन स्क्वायर्ड वैल्यूज़ की ज़रूरत पड़ती है. और लास्ट बट नॉट द लीस्ट आई वाज टॉकिंग अबाउट रिपल पोटेंशियल या रिपल वोल्टेज. रिपल वोल्टेज बेसिकली अभी यहाँ तक आया नहीं है. रिपल वोल्टेज तब आता है जब हम फिल्टर सर्किट लगाते हैं. और फिल्टर का मतलब ये होता है कि जैसे हाफ वेव रेक्टिफिकेशन में मेरे पास जो जवाब आया है वो एसी पल्सेस हैं, एक कांस्टेंट वैल्यू, सॉरी डीसी पल्सेस हैं, वो कांस्टेंट वैल्यू नहीं है डीसी की. तो इस पल्सेस को कम करने के लिए, एक कांस्टेंट वैल्यू अचीव करने के लिए हम मज़ीद इसमें सर्किट मतलब लगाते हैं एक्स्ट्रा कंपोनेंट्स, तो उसे हम फिल्टर सर्किट कहते हैं. वी विल इंशाल्लाह सी दिस इन द कमिंग लेक्चर. तो मैं इसको थोड़ी देर के लिए रोकता हूँ रिकॉर्डिंग को, और नई वीडियो जो है नेक्स्ट इसकी वो प्ले करता हूँ आपके लिए. और आई थिंक इट इज़ इनफ. शायद ये 2 काफ़ी हैं इस लेक्चर में, और नेक्स्ट लेक्चर में इंशाल्लाह बाकी 2 मैं शेयर कर दूंगा. तो वी कैन हैव अ क्वेश्चन आंसर सेशन इन टुमारो इवनिंग अगर आप लोग चाहें तो. अभी तक जो बातें डिस्कस की हैं उसमें से, या जो मैंने इंशाल्लाह मैं जो नेक्स्ट लेक्चर है वो भी, जो नेक्स्ट 2 लेक्चर्स मेरे हैं लेक्चर 6 और 7, उस के पे मुहित होगा वो, तो वो इंशाल्लाह मैं आपसे शेयर कर दूंगा बाय सम टाइम टुमारो। तो फिर हमारा ये वाला पोर्शन ख़त्म हो जाएगा। फिर वो लेक्चर्स हैं जो मैंने क्लास में ऑलरेडी लिए हैं, तो वो इससे मेरा ख्याल है ज़्यादा बेहतर होंगे इंशाल्लाह, इन अ सेंस कि उसमें थोड़ी सी कंटिन्यूटी बेहतर होगी एक तो, दूसरा वो इंटरैक्टिव है, उसमें स्टूडेंट्स के क्वेश्चंस के भी आंसर्स हैं कुछ जो साथ साथ पूछते हैं। तो आई थिंक वहाँ पे आप रिलेटिवली, यहाँ शायद सुनना मुश्किल हो जाता होगा, वहाँ पे शायद नहीं होगा आपके लिए ज़्यादा मुश्किल, बल्कि उसके जो लेटर हाफ है उन लेक्चर्स का, उसमें तो मैंने फिर प्रॉब्लम्स भी साथ करने को, क्लास में डिस्कस करने के लिए मैं टाइम देता हूँ कि आप ये प्रॉब्लम सॉल्व करें खुद, आप खुद सॉल्व करते हैं, फिर उसके एंड पे मैं उसका कुछ सोल्यूशन बताता हूँ। तो वो इंटरेक्टिव है बहुत ज़्यादा, और नेक्स्ट जो पोर्शन है इन लेक्चर्स का। तो मैं आपसे अभी तक, क्योंकि न्यूमेरिकल्स आए नहीं है, तो मैंने आपको कुछ इनपुट आपसे नहीं ली है कि वन वे कम्युनिकेशन चल रही है अभी। तो इंशाल्लाह 7th लेक्चर जो है, मतलब इस लिहाज से जो 5th के बाद 7th बनेगा, और हमारा इस तरह से वो 3rd वीक के जो लेक्चर्स हैं उसमें जो आएगा इंशाल्लाह, तो वो मुकम्मल हो जाएगा पोर्शन जो वन वे कम्युनिकेशन वाला है। उसके बाद 2 वे कम्युनिकेशन होगी, जिसमें स्टूडेंट्स की बातें भी होंगी, कुछ क्वेश्चंस होंगे, मैं उनको आंसर्स कर रहा हूँगा या उनसे कुछ पूछ रहा हूँगा, तो दैट कैन प्रॉबेबली बी बेटर। मे बी आपके लिए अनोइंग होगी कि उसमें आप लोगों के नाम नहीं होंगे, वो जिस क्लास को मैं पहले पढ़ा रहा था उनके नाम चल रहे होंगे, लेकिन आप फिर भी थोड़ा बहुत उससे एंटरटेन हो सकते हैं, आई मीन उसके इंटरेक्टिव इन्वायरमेंट से। तो थैंक यू वेरी मच, और इसको आप पढ़ें इंशाल्लाह। फिर हम नेक्स्ट वीडियो के बाद आपसे एक सेशन होगा, क्वेश्चन आंसर सेशन। थैंक यू वेरी मच, गॉड ब्लेस यू गाइस।